So in the last video, I made a very small mistake here. So this is my comment line, and comment line will not get executed by the compiler, and the time it will take to execute this statement will be 0, not C3 here. So the time taken to execute this particular statement will be 0. Okay, fine. So as of now, we just analyzed everything except the inner while loop, right? Now let us ask ourselves what exactly this inner loop is doing here, the inner while loop is doing here. So this is one of the most critical part of this analysis. The rest of the code is very straightforward. And the most important for you to understand is this inner while loop, because it determines the overall time complexity of the entire algorithm. Now, if you look at the while condition here, the while loop condition, the condition here is a of j is greater than key, right? So it is performing the comparison operation here. Now, let me explain this with a simple diagram. Let's say I have an array E, so I have an array E, and the element AJ. So this is my element AJ, which we call it as the key as part of that algorithm. And I'm comparing this element with AJ minus 1, AJ minus 2, AJ minus 2, AJ minus 3, and so on down to A of 1 here. And also, if you look at an algorithm, I initialize the value of I is equal to j minus 1, and we continue this loop while I greater than 0. That means the loop can run until I is equal to 1. In other words, I would say, we compare the key with each of these elements from aj minus 1 down to a of 1, right? So what is happening inside the while loop? Now let's go and analyze each and every statement what is present in this while loop, right? So at the first line, I have a of I greater than key, so it performs the comparison, right? So in statement 2, a of I plus 1 is equal to a of I, so it performs the shift operation, or that means moving the elements one position to the right. And in the line number 3, I am decrementing the value of I by 1, right? Now to determine how many times these operations are executed, we need to analyze in the 3 different cases. So let me explain all of these cases through a simple example. So this is my case 1. So this is my case 1, and this is my case 2, and this is case 3, right? So in case 1, this is my array. So the given array is already sorted, and assume that this is my AJ, right? A of j. The element is 8, and 8 is already greater than 6, right? The larger element in the sorted position, the 8 is larger element in the sorted position. Now, if you look at in this particular case, how many comparisons we made here? So total we made only one comparison. So I just checked this element is less than equal to this number or not. So how many comparisons I made? I made one comparison, right? So did I move any element to the right? No. The number of swaps is equal to 0 here. So in case 1. Now let's go to the case 2. So in case of case 2, I have an element 4. So my AJ is equal to 4. Now I'm going to compare 4 with an element 6. And 6 is greater than 4. That means I need to move this element to the right. Now again I will go and compare this element with an element 3 here. And 3 is less than 4. So in this case, no need to move this element to the right, right? Now in this particular case, how many number of comparisons I made? I made 2 comparisons. But how many number of swaps I made here? Number of swaps is equal to 1. So I just moved the element 6 to the right position, right? Now let's go and analyze the third case. This is a very interesting case. Suppose my AJ is equal to 0 here, right? Now look at all the elements present in an array compared to this element, right? So first I will go and compare with a 6, then again I will go and compare with 3, then 2, then 1, right? So all the elements are larger than my current element. So in this case, how many number of comparisons will made? The number of comparisons will be 4. And how many number of swaps are required here? Again, we need of 4 swaps. So out of all these 3 cases, I would say this is my best case. So when can I say it is a best case? All the elements are already sorted. No need to perform any swaps here. And I would say the case 3 will be my worst case, right? So compared to this element, all elements are larger. So I need to move all the elements to the right. So in a general, I would say for the given value of j, for the given j, right? So the minimum number of comparisons required is equal to 1. So when is going to happen? So this would happen when a of j is the element is already sorted. So this is my best case, right? What is the maximum number of comparisons required here? Comparisons will be what? So I would say it's a j minus 1. So in case of j, how many number of comparisons are required? So in this case 4, that is nothing but my j minus 1, right? First to j minus 1, this many number of comparisons are required. So what about the swaps? The minimum swaps required while performing this task will be 0. So when this is going to happen? This would happen when a of j element is already sorted out. So this is the best case. So the maximum number of swaps required will be what? How much? Which is equal to j minus 1. I hope this analysis is crystal clear to everyone, right? So for any given value of j, the minimum comparisons will be 1 and the maximum comparisons will be j minus 1, and the minimum swaps required will be equal to 0 and the maximum swaps required will be j minus 1. So these are the very important observation we made through this simple example. Now if you look at the for loop, now the for loop will run various values of j, right? Remember that j runs from 2 to n. N is my length of an array here, right? Now let's go and analysis for each value of j. Let me write it down here. So at value of j is equal to 2, how many minimum number of comparisons required? Minimum comparisons required will be 1, right? At j is equal to 2, at j is equal to 3, how many minimum number of comparisons required? Again we may need of 1. So this will be my best case, right? At the value of j is equal to 4, how many minimum number of comparisons required? Again 1. So let's say at my value of j is equal to n, how many minimum number of comparisons required? Only 1. So what about the maximum number of comparisons? Let me write it down. Maximum comparisons. Now in case of j is equal to 2, how many number of comparisons are required? Maximum number of comparisons required is equal to 1. At j is equal to 3, how many comparisons are required? 2. At j is equal to 4, how many comparisons are required? Which is nothing but j minus 1, right? 4 minus 1, that is 3. Similarly, when my value of j is equal to n, the total number of or the maximum comparison required will be n minus 1 because my value of j is equal to n. Similarly, how many number of minimum swaps required here? Minimum swaps for each of these values of j. So the minimum number of swaps required when the value of j is equal to 2 is 0. J is equal to 3 will be also 0, 0, 0, right? So this is my best case, right? At the best case, the number of swaps will be 0. Now, what about the maximum number of swaps? For each of these cases, when the value of j is equal to 2, so we may need of 1 number of swap. For j is equal to 3, which is j minus 1, right? So 2 number of swaps, 3 number of swaps, and so on, n minus 1, right? Now, if you want to understand how many times this comparison operation will run, you just need to sum it up all of these various values of j, right? So for each value of j, we perform exactly one comparison. So I'm talking about the minimum comparisons. So the total comparisons will be what? 1 plus 1 plus and so on n minus 1. So I would say it will be, plus 1. To total we have n minus 1. So in case of a maximum number of comparisons, so the maximum number of comparisons will be what? So here you just need to add all of them. 1 plus 2 plus 3 plus and so on. At the end we have n minus 1. So total how many number of comparisons required? The maximum number of comparisons required will be, so this is the formula of an arithmetic progression, right? So you might have studied in your high school. So the formula will be n minus 1 into n by 2. So this is the maximum number of comparisons required, right? And what about the minimum swaps? So you just need to add all of them. So 0 plus 0 and so on, you will get the value 0. What about the maximum number of swaps required here? Again, you just need to add all of them. 1 plus 2 plus 3 plus and so on, n minus 1. So that you get a value as n minus 1 into n by 2. These are my maximum number of comparisons required. Right? Yes, I hope everybody clear about this part. Right? Now, if you go and write down all of them here. Right? So for this statement, the minimum number of comparisons required. So what is the minimum number of comparisons required here? So I would say that the minimum will be n minus 1 and the maximum will be n minus 1 into n by 2. And what about the minimum number of swaps required here, which is equal to n minus 1, and this will be n minus 1 into n by 2. Similarly, for decrement operation also run the same number of times as the shifts. So it will be n minus 1 and n minus 1 into n by 2. So sorry guys, minimum number of swaps required will be 0, right? And minimum number of decrement operator will be 0, right? So which we have already calculated here, right? So the minimum number of shifts or swaps required will be 0, right? So now in the total, I would say that the number of comparisons would be n minus 1 and the maximum number of comparisons will be n minus 1 into n by 2, right? Similarly, the number of minimum swaps will be 0 and the maximum number of swaps will be n minus 1 into n by 2 and so on. For each of these lines, right? And I can have some constant amount of time is required. Let's say comparison takes, so this line takes C5 microseconds, this will take C6 microseconds, let's say this will take C7 microseconds, right? So total will be what? So C5 into n minus 1 for our minimum comparisons. For maximum comparison, it will be C5 into n minus 1 into n by 2, right? So minimum swaps will be what? 0 into C6, so the value will be 0. What about the maximum number of swaps required? So the maximum number of swaps will be C6 into n minus 1 into n by 2. So in the case of decrement operation, so the minimum decrement operation required will be 0 and the maximum will be C7 into n minus 1 into n by 2, right? So I hope everybody understand this analysis. Now let's calculate the overall time complexity of the entire algorithms. So earlier we have C1 into n. I need to add all of them to get the total time taken to complete the algorithm, right? So let me add all of them in detail. So again, I will analyze in terms of minimum and the maximum case, right? So minimum means is my best case, the maximum will be the worst case, right? So what is the worst case time taken to complete the entire algorithm, and the best case how much time it will take to complete the entire algorithm. So for minimum, first few lines will be common, right? So C1 into n, second line it will take C2 into n minus 1, and for third line this is the comment line, so it will be 0, you can ignore it, right? For fourth line it will require C4 into n minus 1, C4 into n minus 1. For the fifth line, so if it is the minimum number of swaps, what is the time taken to execute this particular statement? It will be C5 into n minus 1, right? So C5 into n minus 1 and C6 into 0, because the minimum number of swaps required will be 0, and the decrement operation will also take 0, and the last we have C8 into n minus 1, right? So this is my overall time complexity for the minimum case, that is the best case, right? So what about for the max case? So this statement time will be remain same. The first statement time will be remain same, C1 into n, C2 into n minus 1, and C3 into 0 because of the comment line, C4 into n minus 1, and what about line number 5 here? The line number 5 will be C5 into n minus 1 into n by 2, right? So C5 into n minus 1 into n by 2, and again C6 into n minus 1 into n by 2, C7 into n minus 1 into n by 2, and C8 into n minus 1. So this is the worst case time, right? So if you are going to add all of them, you will get the overall time complexity. So remember, C1 is the constant value. For example, C1 could be 1 microsecond here, right? Or C2 could be, let's say, 2 microseconds, or C4 could be 1.5 microseconds. So if you look at an insertion sort algorithm, what we are trying to understand in time and space analysis is, as the input, so as the input changes, how do we determine the time and space? So how do time and space change? Now remember, these constant are independent of my input size. The time required to execute each individual operation like C1, C2, C4, etc., C5, C8 does not dependent on my size of the array. So I would say that it is independent of my value of n. So if we sum up everything in the best case, we can write it down the total time as an plus b, right? So here A is the combination of C1, C2, C4, C5, C8. So these all are my constant. So it is a combination of C1, C2, C2, C4 and so on. Similarly, B is also a combination of these constants. So A is essentially a function of C1, C2, C4, C5, C8. But it's still a constant. Likewise, B is also a constant. Given an array of size n, the only thing that changes is n. N could be anything, right? So n could be 10, or n could be 100, or n could be 1000, or n could be 10,000. All other values are constant here. The remaining all other values are constant. Only the value of n is getting changed. Therefore, in the best case, the total running time of an insertion sort algorithm is an plus b, where a and b are the constant that can be computed using C1, C2, C4, C5 and etc. So as the size of the input array increases, the only variable that changes is n here. So this represents the best case running time. Now let's go and analyze the worst case. So in the worst case, when we sum up everything, we get a term involving this, right? So n into n minus 1. So when we expand, this will produces as n square term, right? So n minus 1 into n. So n square term you will get. So therefore, the total time can be written as, so instead of writing a, I'm just writing down as a dash n square plus b dash n plus c dash here. Here again, a dash, b dash, c dash are the constant derived from C1, C2, C4, C5 and so on. And also we have some kind of a factor, right? 1 by 2 because of the division by 2 in n minus 1 into n by 2. So notice that these a dash, b dash, c dash are different from the constant of A and B here. So to avoid the confusion, I just used the different symbols as A dash, B dash, C dash. So in the best case, the running time of an insertion sort of n elements is an plus b, where a and b are the constant. But in the worst case, the running time is a dash n squared plus b dash n plus c dash, where a dash, b dash, c dash are the constant. Later we will discuss why we write the running time in this simplified form instead of explicitly writing of all of these constants or using this constant value like a and b. We will understand this in the upcoming videos. So far we have analyzed only the time complexity, that is how many microseconds it takes to execute the algorithm. That is what we understood so